Well, as we saw earlier, these kinds of signals and others derived from the computations of the superior olivary complex and the nucleus of the lateral lemniscus converge in the inferior colliculus, where a complete map of auditory space is computed for the first time along this pathway, not just the location of azimuths, but also elevations. The inferior colliculus sends relays up to the auditory division of the thalamus, the medial geniculate complex, and from there the medial geniculate complex projects to the primary auditory cortex. And it's about the primary auditory cortex that I'd like to conclude this tutorial. So the auditory cortex is organized into a core region which is surrounded by a belt of higher order auditory areas. That core region is found along the superior aspect of the temporal lobe. And there's a series of transverse gyri that we find on that superior plane of the temporal lobe that are called Heschel's gyri. And typically 2 or 3 of these gyri are where we will find the terminations of the medial geniculate complex of the thalamus. So that's where we would find our primary auditory cortex and the core division, which is illustrated here in blue. So this primary auditory cortex found here on the upper part of the superior temporal gyrus is where we would find a complete representation of the frequencies that are first encoded down in the basilar membrane. So we have a frequency map of our auditory environment established across the modules that comprise this auditory cortex. The more anterior region responds to stimuli that are encoded near the apex of the cochlea, whereas the more posterior region encodes the higher frequencies that are first transduced near the base of the cochlea. And again, surrounding this central core region is a belt of auditory areas that seem to process increasingly complex aspects of auditory information. Of course, one aspect of audition that is very important in this part of the brain is human speech. And some division of this higher order auditory area includes what we call Wernicke's area. So somewhere in this auditory belt region, we have circuits that are essential for understanding human speech. Not just the spoken word, but also written human language. We call this region Wernicke's area. This region is named after the German physician Wernicke, or perhaps you prefer the pronunciation Wernicke, who described a series of patients that had damage to this part of the brain. And one consequence of that damage is an inability to understand human speech. So Wernicke's area is often depicted as being present in the posterior aspect of the superior temporal gyrus. However, if you consult with neurosurgeons that actually map out our functional Wernicke's area in the human brain during neurosurgical procedures, we find that Wernicke's area might be distributed over a much broader region that potentially extends into the inferior parietal lobule and all the way anterior near the anterior pole of the temporal lobe. Now, that's not to say that all of this cortex is Wernicke's area, but rather there may be key nodes in a lateral temporal network that are critical for understanding human speech. The job of the neurosurgeon is to identify these key nodes and do his or her very best to avoid damaging them in the course of neurosurgery. So, an illustration such as this that points a leader to one particular region and calls that Wernicke's area is potentially a bit misleading. So I would advise you, if you are ever subject to neurosurgery in your lateral temporal lobe, make sure you have a surgeon that specializes in mapping language in these areas, and please make sure that your surgeon maps your languages, not just the language of the surgeon. There have been famous errors made in these surgical procedures in this part of the brain because a surgeon may not have considered the possibility that there may be different nodes in this lateral temporal network that are essential for understanding speech in different languages. That indeed seems to be the case. Those of you that are multilingual, you may have several important nodes in your network that are critical for each of the languages that you have come to understand. So this is a very complex system. It's more broadly distributed than we once thought, and it's an area of ongoing investigation to understand how this part of the human brain is organized and functions. Another important point to make about Wernicke's area is that for nearly all of us, it's present in the left hemisphere. Those that have a functional Wernicke's area in the right hemisphere are likely to be left-handers. Now, not all left-handers have a right hemispheric dominance for language function. It's just that left-handers are more likely than right-handers to show this opposite pattern of asymmetry. Actually, one idea that has gotten a fair amount of interest is that in left-handers, the pattern of asymmetry is simply more random than what is observed in right-handers, where we very consistently find a left hemispheric dominance for language function. Now, that's not to say that there is not specialization of the right hemisphere with respect to language function. Indeed, there is a region in the right hemisphere that corresponds to what we describe, at least structurally, as Wernicke's area. It may be less critical for understanding language than what is present in the left hemisphere, but it could be quite important nevertheless. One aspect of the right hemisphere that seems to be important in language function is prosody. Prosody refers to the emotional content of speech. Damage to the lateral aspect of the right temporal lobe may lead to impairments in understanding the emotional content of speech. So a person with such an injury may be able to understand the meaning of the words in terms of their semantic content, but might not be able to pick up the nuances of emotion that are present in speech. Not only is language lateralized to the left hemisphere for most of us, but there is also a structural difference between the left and right temporal lobes in this region of this auditory belt cortex. The superior aspect of the posterior temporal lobe is a sort of a flat region that we call the superior temporal plane, or the planum temporale, and it appears to be larger in the left hemisphere compared to the right hemisphere. Consequently, the lateral fissure is longer and straighter in the left hemisphere compared to the right hemisphere, where there's often an upward bend, giving the impression of a shorter lateral fissure in the right hemisphere. Well, that difference that we observe from the outside we think reflects this difference in the extent of this superior temporal plane in the two sides, with about 2/3 of us having a larger planum temporale in the left hemisphere compared to the right. Now, it had been thought, and perhaps still there's some truth to this, that this asymmetry in structure relates to the asymmetry in function that's associated with language comprehension. However, the fact that the majority of us, somewhere around 97-98% of us, have our functional Wernicke's area in the left hemisphere, whereas only about 2/3 of us have an asymmetry of the planum temporale, suggests that there must be more going on there. Well, one interesting clue as to what might be going on was discovered some years ago when a study was done of planum temporale size in individuals who were musicians, some of whom had this very special ability called perfect pitch. And this is the ability to be able to discriminate tone or to be able to produce tone of a given pitch and to know exactly what that pitch is. Well, most musicians, professional or otherwise, don't have this ability, but some do. And at least a cohort of individuals with this special talent, this ability to discriminate and to produce perfect pitch, ended up having a larger asymmetry in their platinum temporale region compared to skilled musicians that lack this ability. So there's something about the asymmetry between the auditory regions in the two hemispheres that gives rise to this special talent. And it will be interesting to see if other dimensions of music perception, or perhaps even music performance, might also be related to asymmetries in these parts of the brain. And finally, I'd like to show you just a little bit of data on this point of asymmetry in the region of the auditory cortex, and just highlight some of the specializations that we're beginning to learn about this fascinating part of the brain. As you listen to my voice, there is a greater volume of your left auditory belt region activated compared to your right. So left is greater than right when listening to human speech. And this presumably reflects the specializations that we call Wernicke's area that are manifest in the left lateral temporal lobe. While we listen to environmental sounds, there is virtually no asymmetry in the activation of the two hemispheres, and presumably that reflects the distribution of auditory connections relative to the range of environmental stimuli to which we must respond. Now, music appears to be quite special and perhaps quite different. When we listen to music, what we find is the opposite asymmetry, with right hemispheric activation being significantly greater than left hemispheric activation. In fact, the asymmetry when we listen to music is even greater than the asymmetry that's detected when we listen to human speech, but it's in the opposite direction. And this presumably reflects a broader and more general bias of the right hemisphere towards encoding signals that pertain to human emotion, although that bias is not absolute. So music seems to engage different networks that are lateralized in a distinct pattern compared to those that are being activated right now as you listen to the sound of my voice. Well, I hope you've enjoyed this discussion of the auditory system and this exploration of some of the physiology of these parts of the brain that are so important for our social dynamics as we communicate orally with one another, and so important in the richness of our lives as we experience the environment. Where I am right now, I'm being serenaded by a chorus of toads in a nearby swamp. I've heard the sound of deer and possum in the forest around me, and the occasional call of the owls that are busy hunting their prey here in the darkness of these woods that surround me. Well, that's all been a joy for me to experience. Perhaps you've heard a little bit of that in this audio track on this tutorial as well. Well, I'll leave you with just a little riff on one of my favorite tunes, and hope you enjoy that on your way out.